Again, comparing two variances. Our main objective in these lectures is to use one-way analysis of variance to test claims involving three or more means. Also introduce two-way analysis of variance. So normally when we have more than two samples, at least three samples or more, then we have to use ANOVA. ANOVA also is a parametric test, so we can test the mean. So one-way analysis of variance, here we say hypothesis testing technique that is used to compare means from three or more populations. Again, one-way ANOVA. The analysis of variance is usually abbreviated as ANOVA, and this is the hypothesis. We state both the null and alternative hypothesis. So here we are assuming mu1 equal to mu2 equal to mu3 all the way to mu k. Again, k will be the number of samples we have. Then HA will be at least one of the means is different from the others, at least one. So in a one-way ANOVA test, the following must be true. One, each sample must be randomly selected from normal or approximately normal population. Then the samples must be independent of each other. Then each population also must have the same variance. So one-way ANOVA, first we start with the test statistics, which is equal to the variance between samples divided by the variance within samples. Now the variance between samples, abbreviated as MSB, will measure the difference related to the treatment given to each sample. And again, it's sometimes called the mean square between. Then we have the variance within the sample, which is MSW. Normally we measure the differences related to entries within the same sample. So this variance sometimes called again mean square within, and it's usually due to sampling error. So if the conditions for one-way analysis of variance are satisfied, then we are ready. The sampling distribution for the test is approximated by the F distribution. Then we are ready to do our test. So the test statistics to find F will be MSB divided by MSW. And the degree of freedom for the F test are, for the numerator, the N, DFN means the numerator is equal to K minus 1. And DFD, which is for the denominator, is N minus K. Again, K is the number of samples we have, and N will be the sum of all the sample sizes. So let's follow the steps here, test statistics for one-way ANOVA. So the first step, we are going to find the mean and variance of each sample. So we have the formula as same as in descriptive statistics to find the mean and the variance of a sample. Then we find the mean of all the entries in all samples. So the mean of mean will be the sum of, or the mean divided by total sample. So find the mean of all entries in all samples. So uppercase N will be the total size of all the samples. Let's say if it's 3 samples, then the total sum of all the 3 samples. Then we can find the sum of square between samples, which is SSB. And that will be the sum of NI and the difference of X bar I minus S bar bar. So as we said, S2 bars means the samples, the mean for all the samples. And S bar will be the sample. For example, if we have 3 samples, we may have S1 bar, S2 bar, S3 bar. So SI bar represents the sample mean for each sample. Let's say sample 1, 2, 3. So after we find that, we can find the sum of squares within the samples, which is SSW, the difference of each sample size minus 1 times the variance. So I again, so the subscript I represent the sample number. So if it's 3 samples, then we are going to sum all the 3 samples. Each sample have its variance, each sample have its mean. So we find the difference between one and the sample size. Then we multiply by the variance. So again, n is the sample size, s square is the variance. Then we had all, so n, we may have n1, n2, n3, s1, s2, s3. Now we can find the variances between the samples. So MSB will be the SSB divided by K minus 1, which is the same as SSB over degree of freedom for the numerator. Then we can find the MSW, which is SSW over N minus K. N minus K is the degree of freedom for the denominator, SSW. So then we can find the test statistics, which will be the MSB over the MSW. Now, let's follow the steps for one-way ANOVA test. First thing we do, identify the claim. We have to state our HO, and then we state our H also, the alternative. Then we specify the level of significance, as we said earlier, in most hypothesis testing. The alpha value is given to us, which is the level of significance. Then we identify the degree of freedom. So we have 2 formulas here, degree of freedom for the numerator, degree of freedom for the denominator. So it's K minus 1 and N minus K. Again, uppercase N is the size of all the samples combined. Then we can determine the critical value using, again, our textbook is table 7 for the F table. We know alpha, we know degree of freedom for numerator and denominator, we can find it. Then we determine the rejection. So if we know the test statistics, we know the critical value, okay, we can do it. So to calculate the test statistics, F equal to MSB over MSW. Then we can make the decision. We know critical value, we know the F. So we say that make a decision to reject or fail to reject the null hypothesis. So if F is in the rejection region, then reject HO. Otherwise, fail to reject HO. Then we're going to interpret the decision in the context of the original claim. Now, next we have the ANOVA summary table. A table is a convenient way to summarize the result in one-way ANOVA test. So here we have the variation, sum of squares, degree of freedom, mean square, and the F. Between is the first row, within is the second row. So SSB, we need the DFN. To find MSB, it will be SSB divided by DFN. Within also, we find the SSW. Then we have to find the degree of freedom for the denominator, DFD. So MSW will be SSW over DFD. Then we can find the F, which will give us MSB over MSW. So let's see an example. Here we say a medical researcher wants to determine whether 3 is a difference in the mean length of time it takes 3 types of pain relievers to provide relief from headache pain. Several headache sufferers are randomly selected and given one of the 3 medications. Each headache sufferer records the time in minutes it takes the medication to begin working. The results are shown on the next slide. And the alpha value is given to be 0.01. Can we conclude that the mean times are different, assuming that each population of relief time is normally distributed and that its population variance are equal? So if those 2 conditions is given, normally distributed and population variances are equal, then we can do ANOVA. As we said earlier, ANOVA also is a parametric testing. So this is the data given to us. We have medication 1, 12, 15, 17, 12, medication 2, 16, 14, 21, 15, 9, medication 3, 14, 17, 20, and 15. So we find the medication 1, let's assume that's our sample 1. We find the mean, which will be adding all the values divided by 4. We also find the variance to be 6. Then we find the medication 2, the mean will be 85 divided by 5. And then medication 3, which will be our sample 3, we had all the values were 66 divided by 4. And also from there, we can find the variance for medication 2 and medication 3. Again, here we are using the descriptive statistics formula. So solution. First, we know K is 3 because we have only 3 samples. So N, which will be the sample size of all the samples, 3 samples, will be N1 plus N2 plus N3, which will give us 4, 5, and 4. So that will give us 13. So 13 will be the sum of all the sample sizes. So now we can perform the one-way ANOVA. Again, we state our HO equality, mu1 equal to mu2 equal to mu3. Then HA will be at least one mean is different. Alpha is given to be 0.01. The sample size is 3, so degree of freedom for the numerator will be 3 minus 1. Then degree of freedom for the denominator will be 13 minus 3. So now we can draw the rejection region, and that gives us critical value 2. So next we find the test statistics. In order to find that, first we find the sum, the mean for all the 3 samples, because we don't have it yet. So we had all the 3 samples divided by 13, because that's the, again, size. Then we find the MSB, which is SSB over DFN. To look for SSB, to be the sum Ni, N bar I minus N2 bar I, or square over K minus 1. So we plug in the values. Again, we have 3 samples here. So we have 440 minus 1592 square plus 517 minus 17.92 square plus 4, 16.5 minus 15.92 square. Then we divide by 3 minus 1. So if we do our calculation, we will get 21.92, then we divide by 2, and that will give us 10.96. Now, to find the test statistics, the following must be calculated. We need to find MSW, which is MSW over DFD. We plug in the values, and we look for the MSW, which will be 7.3. Now, with the new MSW, we can find the F, which will be 10.96 divided by 7.3. And that gives us roughly 1.5. So here we have the F to be 1.5. We can make a decision now. We are going to fail to reject HO. So we say there's not enough evidence at the level 1%, at the 1% level of significance to conclude that there's a difference in the mean length of time it takes the 3 pain relievers to provide relief from headache pain. So let's try next example using TI-83/84 calculator, Texas instrument. So here we have 3 airline companies offer flight between Corridon and Lincolnville. Several randomly selected flight times in minutes between the towns for each airline are shown in the next slide. Assuming that the population of the population of the flight times are normally distributed, also the samples are independent and the population variances are equal. At alpha equal to 0.01, can you conclude there's a difference in the means of the flight times? So here we have all the data given to us for airline 1, airline 2, airline 3. So we state our HO and HA. Always HO is equality, M1 equal to M2 equal to M3. And HA, at least one mean is different. So first we can store the data in lists L1, L2, L3 here using technology TI-83/84. Then we say if P value is less than alpha, then we are going to reject HO. So there's enough evidence to support the claim. You can conclude that there's a difference in the means of the of the flight times. So next is the two-way ANOVA. In two-way analysis of variance, we say the hypothesis testing technique that is used to test effect of two independent variables or factors. So the hypothesis testing technique that is used to test effect of two independent variables. Previously, it's one-way ANOVA is one independent variables. So here we have a gender. Within the gender, we can have male and female. Then when we look at the type of medication, we have 1, 2, and 3. So one thing we should know, the effect of one dependent variable on the dependent variable. And also we have interaction effect. Interaction effect means the effect of both independent variables on the dependent variables. So hypothesis testing for the main effect will be gender has no effect on the mean length of time it takes a pain reliever to provide relief. HA will be gender has an effect on the mean length of time. So here we say the type of medication has no effect on the mean length of the time it takes a pain reliever to provide relief, or type of medication has an effect on the mean length of time it takes a pain reliever to provide relief. So two-way ANOVA tests calculate the F-test statistics for each hypothesis. Then it's possible to reject none, 1, 2, or all of the null hypotheses. This also can use a technology tool such as Minitab to perform two-way ANOVA. So use one-way analysis. In these lectures, we use one-way analysis of variance to test claims involving 3 or more means. Also, we introduce two-way analysis of variance. So again, wish everybody the best and thank you.